Hello everyone, I am Ferdubati and this is our last lecture on supervised learning. So the topic of this lecture is artificial neural networks, and these are the topics that we will cover. So I'll talk about neurons, which is a basic mathematical function in neural networks, and the links that connect different neurons at different layers. We will discuss about activation function, which is a critical aspect of neural network. There are many activation functions, but we'll discuss about perceptrons and sigmoids. So those are the two simpler, commonly used ones, particularly sigmoid perceptron. We don't use perceptron any longer in real world problems. And another important aspect of neural network is the architecture that includes the structure of the network and how many neurons, how many layers, and how do you connect each one. And those are, we won't get to the details of that because there is no simple formulation that dictates how you design your neural networks. It depends on the type of data, the type of problem that you deal with. But it's an important aspect of designing your neural networks. Learning, we will use gradient. We will discuss gradient descent, which is a very widely used technique to deal with the optimization aspect of neural networks. Now, in this lecture, we don't discuss about backpropagation, which is what really makes a neural network powerful. The ability to propagate the activation as well as the forward and the error backwards. So we will cover that in a separate topic, but backpropagation is very important. Okay, so the basics. Artificial neural network is composed of simple units. We call them nodes, and they're also called neurons. Each of those perform a mathematical function. So a neuron is nothing but a way to compute a mathematical function in the network. So the different neurons are connected through links and they carry information. So each neuron performs some computation and that is transferred to the next neuron through links. So the links are nothing but just a line that connect the different inputs. They also carry weights, and the weights dictate the amount that is assigned, the relevance of that input to the neuron. So they carry information according to the weight assigned to them using training rules built from data. So the weights are the learned parameters, and they determine how relevant or the amount of information carried by that input. Okay. The last bullet is the biological aspect of neural network. For the most part, the machine learning science have moved on from this resemblance, but the initial inspiration of NN was to mimic how humans think, how the brains function. So in a way, to design intelligence systems, right? Now, like I said, many people have reservation about really to what extent we understand the brain to be able to mimic an artificial neural network. But it was important, the original inspiration came from that. Okay, so let's start with discussing about neurons. Okay, so like we said, it is an elementary or the basic unit of artificial neural networks. It's a mathematical function. So here, as you can see, there is one neuron, and this neuron takes inputs, three inputs, x1, x2, and x3. These are the inputs from, it could be originate from the data, or it might be an output from a previous node or a previous neuron. So it receives one or more inputs. And it does apply different weights for those inputs. So in this case, x1 gets weight 1, weight 2 is applied x2, and weight 3 is applied to x3. So a linear combination of this is entered into the neuron. So it passes the sum through a nonlinear function. Now, we haven't discussed about activation function. So the combination of the three things are transformed through a function called activation function. And in subsequent slide, we'll cover about perceptron and sigmoid, which are the two types of activation function. But effectively, what neuron does is it takes input, applies different ways to those inputs, and then takes a linear combination of those and then transfer it through an activation function. So that is what a neuron does. Okay. Now, let's discuss this further in the context of a perceptron activation function. So a perceptron is now, I have to start by saying that we no longer use perceptron for real world application because they are difficult to train, or to learn parameters using a perceptron activation is not easy. But in the 1950s, perceptron used to be the ones that make up a large population of the neural networks. However, recently there are other activation functions that are easier to train, and we will cover those when we compare perceptron with sigmoid. However, it's easier to explain how neural networks work using a perceptron, so that is what I'm using. By the way, most of the content that I use in this presentation come from a book which you can find online. It's called Neural Networks and Deep Learning by Michael Nelson. I find it's easier for new students that are not familiar with neural networks. Although I have other materials in this, but to the extent practical, I stay consistent with the way he uses symbols and formulas and notations. I tend to use these notation to be consistent. So going back to perceptron. So in this particular case, it's a binary. Perceptron is a binary classifier. Okay, it's an algorithm of a binary classifier, which means it learns a linear separator. So in this graph, we have a two-class problem. We have a blue dots from red dots, and then this is the learned model, the linear separator that separates the two classes. Now this is a clean example. In real world, it doesn't quite work this way. However, to explain the concept, once you train the neurons, the perceptron, identify the optimal parameters that are the weights. So you define these, and this separates the two classes. And the equation explaining these linear separators are right here. So it's a product of the weights and the input plus a bias term, and this equals 0, and that explains that this linear separator. So instance of one side of the hyperplane are represented by a perceptron output of a 1, and those on the other side by 0. It's not, sometimes you find books that one side is represented by 1, the other side represented by -1. There's no difference. Okay, so that is perceptron. It's a linear separator of a binary class. Okay, so how does it work? So here, similar to what we covered in the neuron case, the process of learning a neural network is determining an optimal set of weights that gives rise to an output that is very close to the desired output. Remember, this is a supervised learning. Okay, in the context of supervised learning, you have desired output we call targets. Those targets are known. Okay, the learning involves finding all the parameters that defines the network that gives rise to an output very close to the desired output. Right? Anything different is considered as error. Okay, so in the case of perceptron, that output is determined by a threshold. So these are inputs. We have n inputs. Okay, those n inputs are fed through a link to a mathematical function, so to a linear combination, by applying weights. So for each one of the inputs, we apply different weights, which will be learned, and then they are combined through a linear combination. We take the sum of those different things, right? The sum of the product of the input and the weight. Okay, and we apply a bias term to that, and that aggregated value is transformed through an activation function. In the case of perceptron, the activation function is a step rule, and we will cover what a step rule is. So we apply a step rule to the aggregates of the inputs and the weights, as well as the bias, and then we decide what the output is based on a threshold. So we determine a threshold value, and then if the linear combination, so in this case the sum of the product of the weights and the inputs, for that J is a neuron. That is that particular neuron. In this case there are 3 inputs and 3 weights, and that is what this explains. If that aggregated value after passing through activation is less than a threshold, some threshold, then it belongs to one class. If not, it belongs to the other class. Okay, that's how what an activation function of a perceptron means. Okay, it's in a step rule. Below some threshold, it belongs to one class, and otherwise to the other class, and it's a binary classifier. Okay, so here in this case, when you have multi-layer perceptron, that means multiple neurons connected in this fashion. So here you have inputs, again x1, x2, and x3. That's an input layer. The input layer, the neurons on the input layer, they don't do any mathematical function. Remember we said a neuron, a true neuron does some kind of computation. Here they just take inputs, right? So these are the input neurons. Then in this particular structure, we have one hidden layer, and we will talk about what layers, how you design hidden layers. But here we have another layer we call hidden layers, and then these are neurons. These are the neurons that actually perform some mathematical function, as we discussed earlier. Okay, and then the output of these neurons are fed into an output layer, neuron in the output layer, and then we compare the result to a threshold, and that's how we determine whether that particular instance in the example set belongs to one class or another class, right? We will still have to compare that output with a desired output, and if it is not correct, then we have to adjust the weights and the biases in order to get close to that desired output. But this is how you would apply multiple perceptron for making more complex decisions. So here, so how we apply the step rule, which is the activation function for perceptron to classify outputs. Now, as I said, kind of discussed this in the earlier slide, where the sum of the combination of the weights and the input for that particular neuron, and then pass through the update rule, which is the step rule. If that result is less than some threshold, it belongs to one class, otherwise to the other. So in the learning rule, so the output, this particular output is compared to a known output or the desired output because this is a supervised learning where you have a desired outcome and then the result is compared to that. Okay, if you need to adjust the weights further, then you have to compare the result. And so if it doesn't match, the error is propagated backward to the weight adjustment. This gets into backpropagation algorithm that we won't cover much in this lecture. But yeah, that is determined by once. So you go through the feed forward uh, phase of the neural network learning process. Feed forward means transferring all the activation from one neuron to another neuron in the forward direction to the output. And once you compare the result, and if that is not close to the desired output, then that's error, and then that error gets propagated back in the network. And that process is a backpropagation learning algorithm, which is important, and we won't cover it in this lecture. Okay, this is an alternative representation of a perceptron. So the earlier one shows that the indexes, so in this case, the sum of the weights and the inputs on the J's neuron, right? Now, it is okay in this aspect because we're dealing with very simple cases, but neural network deal with a large number of variables, a large number of weights, and this representation becomes cumbersome to deal with. So better representation is using a matrix formula for representation. So this is a dot product. This is effectively a linear combination, which is exactly the same as it takes a weight vector times the input vector, and the product of the two gives you effectively the same thing. So which is represented right here. This is a weight vector. This is the input vector. Okay, one is row vector, one column vector. The product of the two gives you effectively the same thing. Okay, like I said, this becomes quite handy when you have large number of variables. As a matrix, the weight matrix particularly becomes really unwieldy when you start dealing with hundreds and thousands of variables and weights. Just an alternative representation to make the formula a bit easier to manage. Here, the threshold was in the previous formula. We were comparing with the threshold. This one just moves the threshold inward. So, and then it's just a different representation. So you take the product of the two, you add a bias. What we call the threshold is a bias. And if that is less than 0, less than or equal to 0, belongs to 1, belongs to 0 rather, and belongs to 1 otherwise. Okay, so it's an alternative representation of what we looked at earlier. So the bias term, there is a different interpretation of the bias term. Is roughly a measure of how easy it is to get the perceptron to fire. Okay, which means if you have if the bias is higher, the perceptron outputs 1. Okay. And another way to look at it is maybe the bias is an offset from the origin. If you just want to visualize that, is what is the offset of the separator? It is proportional to that value. Okay, now there are some, like I said, we use perceptron to just be able to explain the concept of neural networks. In general, they're difficult to train because of their they tend to jump. Okay, because of that step rule. However, in the 1950s, perceptron used to be the main vehicle for training neural networks, and people realized that the limits of applying perceptron for real-world application, because they're very difficult to train. So we don't, for real-world application, we don't use perceptron. We use other activation function. So in general, the concept is the way we learn the parameters or find the optimal values of the weight is by tweaking at each step of the training process, right? We change the weights by a little bit and the bias by a little bit in order to change the weight, the final output a little bit. So we want to get slowly close to the desired output. We don't want to jump, right? Because it's kind of an optimization problem. We like to get the global optimum. However, a perceptron, in the case of the perceptron, a small change in the weights and the biases gives rise to a big change in the output, which is exactly what we don't want to do, right? You might miss the global optimal if you jump. And this becomes a bit clearer when we go through examples on gradient descent, okay? So what we like to have is a bit change, a small change on the weight. So weight plus change of weight. So we are tweaking or adjusting the weights as well as the biases. And we want that to result in a small change in the output. Now, not a big one, but a small change. So a small change in any weight or bias causes a small change in the output. That is a desired state, and in perceptron it's hard to do to achieve that. So the alternative is one. This is one alternative is a sigmoid function. Okay, a sigmoid function, unlike perceptron, can actually take real values between 0 and 1. So if you remember in the perceptron rule, the output is compared to a threshold value, and if it is less than that threshold, it belongs to one class, otherwise to another class, right? So there is nothing in between. It's a jump between the two classes. In the case of, so that is the perceptron step rule. In the case of a sigmoid function, so this is a sigmoid function, and this is 1 over 1 plus a exponent to the variable. So here we have inputs similar to what we discussed earlier. We have inputs x1, x2, and xn. We apply weights to these inputs, and we aggregate them. We apply biases. We transfer through an activation function. Now the activation function is not a perceptron. It is a sigmoid function in this case, okay? And then that gives an output, right? So here we put that aggregated value. So z is the output, that output. So here you can see 1 over 1 exponent to the whole thing. So minus sum of the product of the weights and the inputs to that neuron, and minus the bias. Okay, so that is a transfer function, the transformation that we do through the activation function. Okay, let's discuss about some of the nice properties about sigmoid function. Okay, first of all, is a smooth function. In general, in mathematics, when you have a smooth function, it's good, right? You can take derivative of that function. It's easier to find the optimal values and that. So it's a good property to have a smooth function. Okay, this is a sigmoid. This is a step function on the other side. So the step function means it's one class or another class, and it jumps from one class to another abruptly, as opposed to this case in a smooth transition from value to another. So when you look at the two graphs here, is the only difference really is in intermediate values, right? Anywhere from -4 in this graph, -4 to around 4 is where is the difference. In the sigmoid case, you have a value somewhere. Let's say when it's 0, it is some value right around here. But here, right after you pass a 0 point, it jumps. Okay, anything below 0 is 0 for the step function, and anything above 0 becomes 1. But for the higher values, they're effectively the same. For larger values of x in this graph, both output the same. This 1 and this approaches 1 as well. The same thing for large values of negative values. This gives you 0 as well as this gives you 0. So the key difference is on the intermediate values, okay, modulus values of the input. So here, as z gets larger, remember this is what we plugged the aggregate of the neuron output. The output of the neuron is entered in this value. So as z gets large, that's in the positive direction, because this is in the bottom, then the whole e to the minus z term becomes 0, right? It approaches 0. That means the actual function, because it's 1 over very small number, approaches 1, right? So the bottom becomes 0. So it becomes this term, this particular term becomes 0, 1 over 1. Effectively, the approach is 1 over 1. That equals to 1. Okay. So for large values of z, positive z, you approach 0. On the other hand, for large values of negative values, so minus of negative z, it becomes a very large positive. It approaches infinity. And then, so 1 over a very large number approaches 0. So for large negative values, it becomes 0. Okay. Obviously, in the state function, we just compare it to a threshold value, and anything below the threshold value is one class, and becomes the other class otherwise. Okay, so those are the main differences between a perceptron and a sigmoid. By the way, sigmoid is not the only type of activation function. There are others that are in some cases simpler to work with, but this is just to explain not exactly the actual form, because that's not what is important. And the importance is in the smooth transition of the function. Okay. So due to the smoothness of a sigmoid, you remember the challenge that we discussed is when we make small tweaks to the weights and the biases, perceptron jumps in the output. But because of that smoothness, perceptron sigmoid function actually results in a small change in the output. That is, the output as a result of, so this is a partial derivative. For those of you not familiar with partial derivative, this is just form of derivative, taking derivatives of a function. But when you have that function has multiple parameters, when it's a function of many variables, then you have to, the way to do the derivative is by holding variables. So when you take the derivative of one variable, you have to hold the other variables constant. So the way you do that is using partial derivative. So we have two variables here, weights and biases. So this shows that the partial derivative of the output with respect to the weight, okay, as a result of that change, plus the partial derivative of the function with respect to the bias as a result of the change in the bias. Okay. So the sum of it's effectively the same thing that we discussed, but this is the change is represented here as a partial derivative. But the key thing here is the change in the output is a smaller, right? It doesn't jump, only a small changes. Again, it's still a linear function of the weights and the biases, because it's still a linear combination of the things. That's still the product of the weights and the bias. No, the products of the weights and the inputs plus the bias. And as I said, there are other smooth functions that are simpler to use. Again, it is not the actual form, it's the shape that is more important. And another byproduct of a sigmoid function being smooth, that it doesn't jump from one output to another, you can actually apply it for predicting continuous values. You can use for classification, obviously, because now you can dictate, still you can apply that logic of if the output is less than some value for the purpose of classification, but you can also use sigmoid function for predicting continuous values. Okay, so earlier I indicated that another critical aspect of neural network, in fact, one of the challenging aspect of neural network is how to design an architecture that is optimal, right? There's so many possibilities in terms of layers, in terms of hidden neurons and layers and the connection. So it is not trivial, by the way, and that is what makes partly what makes training neural network more challenging. So here we have inputs. The number of neurons in the input layer is dictated by the number of variables you have in your data set. That's more or less set, right? So you need a neuron for each input. So that's fixed. Now, the most difficult aspect is determining how many hidden layers you're gonna have and how many neurons for in each hidden layer. And there is no one and simple and fast rule that can work for every scenario. So uh, and it's also those values, number of neurons and the number of neurons in those hidden layers are not parameters. You cannot learn them like the weights or in the bias. They are called hyperparameters. That means you apply some kind of heuristic to determine optimal value that allows you to train the model or the network. Okay, so there are some heuristic, but I know that this is an important aspect of it, and so that's in fact one of the things that separates traditional neural network from deep learning, where you have layers, multiple layers on the hidden layer, and the way the neurons are connected a little different. But again, like I said, this is an important aspect. So this is what we call the architecture of the neurons, which dictate the number of neurons in the hidden layers and the number of hidden layers and things like that. The output is also more or less fixed. It is dictated by what you're predicting. If you're predicting, for instance, a binary value, then one neuron can do it, right? If you have multi-class problems, one way to achieve it by having neurons for each class. So you will have multiple neurons for multi-class problems. But the main variable is the number of hidden layers and the number of neurons in each hidden layer. So here this says, unlike input and output layers, designing hidden layers isn't simple, but there are some heuristics, some design guidelines. Okay. Now, learning. Okay, now let's start with the learning aspect of neural network, which is probably the most challenging. And when people tend to characterize neural networks as black boxes, because it's not easy to understand how the parameters. When I say parameters, the parameters are the things that we actually learn. Okay, the process of learning determines what is the optimal values of weights and biases. So that would be parameters. Okay, so the way those are determined in neural networks is not straightforward, especially when you apply deep learning, when it might involve millions, in some cases billions of parameters. So that's what people refer to as black boxes. So this is, again, being a supervised learning, there is a desired outcome, right, that we want the model to mimic for future examples. So that we have a training sample, and we want to train the model so that the parameters are such that the output is close to the desired outcome. So we do have annotated training sample. So if you remember, this is an optimization problem. And if you remember from our linear regression module, so what linear regression does is it is also an optimization problem, right? We apply least square to minimize the sum of the square losses, right? So the coefficient, the parameters are determined by minimizing the square loss function. So effectively the same, at least for one loss function. So we minimize smooth loss function, right? That's why sigmoid was important. It's because it's kind of hard to find the minimum values for perceptron. So it's easier to work with a smooth function. So here we're using a quadratic. It's just an example. You can use there are other loss functions. But by the way, the book that I use primarily for this lecture uses cost function, but they're the same thing. In some literature, they're called cost function. In some cases, loss function. But effectively, what it is the thing that you try to optimize. In our case, the thing that we try to minimize, right? By minimizing that function, we find the values corresponding to that. Like the parameters are dictated by minimizing that function. So similar to the linear regression case, this quadratic loss or mean square loss, it takes the difference of the desired outcome, which is y of x in this case, and the activation. Remember, the output of the neurons is a bunch of neurons is an activation function, because you aggregate the result, it takes the product of the weights and the inputs and transforms to an activation function. Okay, so that is the output, and then you take the square of that and you sum over that all the inputs. Okay, and then you take the average. So effectively, the mean squared error. And here again, we say that the cost is the C is the cost function, which is, or the loss function, which is a function of the weights and the biases, because those are the things that we change. Other things we don't change, right? The things we actually change in order to find the optimal values of the loss function is the weights and the biases. So that's why it is the loss function, or the cost function is it's a function of the weights and the biases. So here this is a weight W is weight vector, B is the bias vector, and it's a sample size in the training data, and is the output vector is the activation. Okay. So as again, the purpose of the training is to get close to the desired outcome. So as that means we want the activation, the output very close to the desired outcome, which means we want the difference between the two be 0. So as y of x gets close to a, the loss approaches 0. So the goal of minimizing C as a function of the weights and the biases. Okay, so that is a framework of learning. Now, once we have that context, let's discuss about gradients, which is a very powerful technique that allows us to find the optimal value without fully applying calculus. That's a derivative, without taking derivative function. Because applying derivative for real-world application neural network, where you have to deal with a very large number of variables, a large number of parameters, is not trivial. It involves quite a bit of computation. It's resource intensive. So there is no, so this thing, the training is not done analytically, and that's primarily the reason why they tend to be black box model. There is no simple formula that we can apply to determine the weights and the biases. Okay. So the gradient descent is a way of solving that minimization problem. Okay, again, don't forget that the key is to find an optimal value, or the lowest point of that loss function, the thing that minimizes that loss function. Okay, so gradient descent allows us to do that without applying the full, without using analytical function. So now let's discuss about what gradient descent is using a simple example using two-dimensional vector. Okay, two-dimensional problem by minimizing the loss function. It's a generic problem in the sense that it doesn't have to be tied to weights and biases. Now, gradient descent is used in a lot of application. It's not just unique to neural networks. So think of this surface right here. So it's explained by three dimensions. So the first dimension is a variation. That's a vector of 2, vector 1. So the vector has two spaces, two components rather, or two dimension, v1 and v2. So as a function of the two, the third dimension, which is the cost of the loss function, right? So v is a two-dimensional vector, and the goal is to find a global optimal on this surface, okay? So assume a ball rolling down on this surface, right? Yeah, so you can start randomly from every location, and then you move the ball on the surface from step to step until you get to uh, uh, the global optimal. The lowest point is on this surface, okay? Again, this is a trivial example uh, just to explain the concept of gradient system. So it says assume the function is a kind of a valley. So it is not straight space, but it has a valley, the lowest point. And so imagine a ball rolling down the slope of the valley. So the ball will eventually roll to the bottom of the valley. And okay, there is, if you think about physical characteristic, there is, gravity, so it will go to the lowest point. But we're not gonna get into the physical aspect of this problem because there's friction, there's momentum. We don't deal with that aspect here. Although the newer models, like deep learning, parameters corresponding to those. So if you choose random point, the starting point for the ball, and simulate the motion as the ball rolls down, you can explain that using derivative. So let's go further and explain how that happens, okay? How we can explain the movement of the ball across the surface. So to represent the problem mathematically, we use partial derivative to explain the ball's movement, okay? So think about it, as a ball moves, now this is a two-dimensional problem. The third component is a cost function, okay? So as the ball moves a small amount in v1 direction and a small amount in v2 direction, the c changes, right? As you move on the surface, you are approaching, that means if you go downward in the downward movement, you approaching to the lowest point of the cost function. That means the c changes at each movement, okay? So the way to characterize that is using a partial derivative. So the partial of the cost function with respect to change in 1, okay, and the partial derivative of the cost function with respect to of change in the direction 2 or v2, okay. Now we call that the change vectors because there is a magnitude of change. It's the amount of the movement. Also, there is a direction aspect of that, right? In what direction, by what amount the ball moves, okay? So to achieve a downward movement, remember, it's an optimization problem, particularly it's a minimization problem. So we gotta make sure that we have to go in the direction of the lowest point. We don't want to go the opposite direction. So the change in vectors are the change in v1 and change in v2 because this is a two-dimensional problem. So we have a vector of changes, okay? And this is a transpose. A transpose means it's a column vector. And this is a gradient. So the gradient is as a partial derivative. The partial derivative with respect to v1 and the partial derivative with respect to, again, this is a column vector. That's why you see the transpose here. Okay, those are the terms that are important to determine the movement of the ball towards the lowest point. Now the question is, how do you determine the amount by which you change? Okay, so the change the vector, the v1 in v1. So how do you determine delta v1 and delta v2? So as to make sure we are not going in the opposite direction. We want to go in the negative because we want to minimize. See, we have to go in the negative direction. That means it's less than 0. So here is again the gradient vector with respect to of two of the components, and the change in the loss function is proportional to the gradient. So the amount of the change, by how much we change the output is proportional to the gradient in the change in the vector, right? So it is a product, it's proportional to the product of the two functions. So that means the gradient, this gradient term, relates the change in V into a change in C. So we're gonna substitute that value in the next slide. So if you assume that the change in the vector, so the amount of the change in the vector is a product of some small quantity called a parameter. It's called a learning rate. That's another hyperparameter that is important for training or learning neural network. So if you take the product of that with a gradient, right? This is effectively what it is, right? The change in the direction is a product of the two. That we can substitute the change in V in the previous function right here, and that gives us this, okay? So if you replace that in here, right here, it gives us the product of the two. And that gives us a gradient squared times that small learning parameters are negative with that. That guarantees that because it's a square component on the term, there's always be less than zero. And that ensures that the direction in which we progress towards the minimal values of the loss function, so that we're not going in the opposite direction. So you got to make sure that the change in C is less than zero. So in the case of our ball analogy, so we move the ball from V to a V prime, the new location, by changing V, by taking the difference of V and eta times change in C, okay? So that gives rise to the new vector location. So that hopefully gives you the intuition about gradient descent. We haven't discussed about how you apply that to the weights and the biases, but that is how gradient descent is. It tries to give a way to find an optimal value or a minimal value of some function called loss function, okay? So this is a pictorial representation of how it would work. So in our analogy of the ball moving on the surface, you start somewhere randomly where you move on one step, you update the V, you find the gradient, and you move in one direction, in this direction. And then the next step, you change again, you calculate the gradient, and then you move to this point. And you keep going this until you get to the optimal, the smallest value of the loss function. So we use the update rule. Remember the update rule is this right here, where you move from one location to another location on the surface. So the gradient descent repeatedly computes the gradient and moves in the opposite direction. Again, the reason why you have to move in the opposite, which is negative direction, is you are minimizing the problem. You're not maximizing it. Okay. Again, as I said earlier, this is in any way indication of real physical motion, because real physical motion you have to account aspect of other physical realities like friction, gravity, momentum. So we haven't discussed that. This is just to explain the intuition of gradient descent. Although deep learning and some latest algorithms actually have terms corresponding to momentum and things like that. Okay. Now we explain this into dimension, but you can easily extend to the multiple dimension. There is nothing mysterious about it. If it applies for one dimension, you can apply it for multiple dimensions. It's kind of hard to visualize in higher dimension, but now the terms are still there. The changes, so instead of 2 dimension, you will have, let's say, m variables. That means you have the vector will have m components. So that makes the change vector. And then the change in the cost function will become effectively the same thing that we had earlier. It takes the product of the gradient and the change in the vector. And so the gradient has vectors the component, the size of which is still corresponding to the variables, the number of variables. Okay, you have so m size gradient vector. Again, the transport is to indicate that is a column vector. So the same thing that we applied earlier. The change in vector is a product of some small learning parameter called eta here, and that is multiplied by the gradient, gives you this. And this is the update rule to move from one direction to another per one step, v to v prime. You take the difference of the v, original location, and the product of the eta and the gradient. Okay, so this is application of the gradient rule or gradient descent for not just two variables but extending to higher dimension. And this is also the same thing. Now, how can we use this thing? We were explaining the intuition of gradient descent in generic term using vectors, right? So how do you apply that for updating weights and biases? Because those are the things that we want to change, and we just want to make sure that the changes we make to the weights and the biases are in such a way that they minimize the loss function. So this is effectively the same thing that we discussed for the case neuron. The weight change from the case to the case for the weight prime, the updated value of the weight, we just take the difference of the current weight for that neuron and take the eta value. Again, this learning is a learning value, or it's a parameter that is it's a hyperparameter that needs to be determined through heuristic means. You have to try different combination of things to determine an optimal value, but in general it's a very small value. So the product of that and the gradient, the partial derivative of the cost function with respect to the weights, okay, that is the update rule. And the same thing for the bias. So this is how we would apply gradient descent in order to update weights at every step until we get to the optimal value, both the weights and the biases. Okay, so we find the minimum of the loss function by repeatedly applying the update rule, right? Okay, so gradient descent is what allows us to find the optimal values of the parameters, the weights and the biases. And then we don't, so that's why we don't apply, for the reason that I explained earlier, because it's not trivial to apply analytical function to determine whether the optimal weights and the optimal biases. So this is the way we do it. Now, in the gradient descent, the gradient is, so even after you do that, there's no guarantee that you're approaching the optimal value, the desired outcome. So the error is introduced, and then you have to backpropagate the error in order to further tweak the weights. And that is what backpropagation is for, right? It applies gradient descent and then to find the gradient of the loss function, but you have to still adjust the parameters further based on the error terms, right? You compare the result and then you backpropagate the result back for further refinements of the weights and the biases. Okay, now the thing that we have explained so far is, so you have to calculate the gradient for each instance of your training sample. So you have a training sample, you have to calculate so for the quadratic loss that we've discussed, we have to calculate the gradient for each instance. Now, when you have a large training sample, which is typical for very complex problems in domains that requires large data sets, it becomes expensive. It's not trivial to calculate. It's not computationally feasible to calculate for the gradient for each instance. So there is this thing called stochastic gradient descent, which is nothing but you split into the training sample into m different samples, smaller samples, and you calculate the gradient. Instead of for individual examples, you calculate for those small samples, and you take the average of that. Okay, and the average of that is the same as calculating the gradient for each instance and taking the average. Okay, so that minimizes or reduces the amount of computation or the number of gradient calculation that you have to perform. Okay, so this shows that it's called mini batch, and then by the way, that's also becomes another hyperparameter. You don't learn this. So the only thing in neural networks we actually learn are the weights and the biases. Everything else should be part of input that in the learning process. So what is optimal mini batch becomes an hyperparameter. You have to try different combination of values. You don't know. You don't learn the mini batch. What is an optimal value of learning? It's not part of the learning the network. It is a hyperparameter that should be determined. Well, you have to try different values, just like the learning rate, just like number of neurons and the number of hidden layers. For m random samples, so you have x1 to xm samples, and you calculate the gradient for each one of them, and you sum over and divide by the m. That gives you the average, and that is approximately equal to doing it on individual instances and taking the average, right? If you calculate the gradient for each and take the average, we have to divide it by n. So this is saying that it's approximately the same as taking the average for each sample and taking divided by m. Okay, so that is a gradient. So that's what's called, it's a variation of gradient descent called stochastic gradients. Okay, so yeah, this is saying effectively the same thing. We take the average of the samples, the gradients of the samples. Now, I think throughout the discussion I kind of mentioned about that there are other variation of gradient descent, and that what you will deal with in data 640, where when you learn about deep learning, we only covered here the perceptron and sigmoid. There are other activation functions and the variation of the gradient descent that's used. Okay, so second bullet says that for a refinement in the context of our analogy of the ball rolling, you may need to include parameters that represent realistic physical characteristics such as friction, momentum. So we don't deal that in this class, but know that there are some enhancement to those terms. So in some cases that may require second partial derivative. So it's tricky when the number of parameters are large. Okay? And I strongly suggest you that read, it's like I said, it's online, it's available online, a book by Michael Nelson. It's called Neural Networks and Deep Learning. It gets a bit complex as you progress through the chapters like backpropagation, deep learning. But you can, in some cases, you can skip those chapters and still be able to understand neural networks and the mathematical aspect of it. So these are some references that I've used that you may want to consult, and so the other aspect, the backpropagation, we will cover that in a separate lecture. And any question that you might have on this topic, we will discuss in class. Thank you for attending.